Okay, now today ఇవాళ మనం will see the shell elements. Okay, so for this we are going to follow this particular example, pinched cylinder. Pinched cylinder means you are going to catch the cylinder exactly in two places, one in the bottom and another in the top. Exactly in this particular, you are going to catch the. Assume that you are catching a tube with two fingers only. That is nothing but pinching. Pinching means you're going to pinch it, you're going to catch it two fingers with pressure, with a large force, right? So that is nothing but you're pinching. Here in this case, we are actually catching a pipe, okay? And where are you exactly holding it? In the midpoint, okay? You are exactly holding it at midpoint here, okay? Like take it something like this. When you're doing some inspection or so, you're going to hand hold the pipe into two beams, kind of like two punches kind of things. Point, 2 point. So that is nothing but your pinching here. This is the pinched cylinder. Okay. Now we have to perform analysis on this particular cylinder model. I'm going to make analysis. See, we are exactly holding it at the mid length. Okay. Now for this, if you observe, this particular pipe, we are holding it exactly at the midpoint. That means the pipe is symmetric with respect to the three planes, right? Assume that 3D. Okay, we have a XY plane here, YZ plane, and ZX plane. Now, exactly the coordinate system is on the centroid of the cylinder. Okay, so in other words, it will be symmetric with respect to the three planes. Origin is at the centroid of the cylinder, so with respect to three planes, we are going to have symmetry. That means we are going to, if we are to perform the analysis of this, take 1/8 part of the cylinder, okay, and perform the analysis by applying symmetry boundary conditions. Here, when you are applying symmetry boundary conditions in 3D, you have to apply it on nodes only. Lest it will cause a heavy, it will give a heavy error. And also, observe that when we are applying symmetry, so there are 4 parts on the top surface which the load is being taken, and 4 parts on the bottom surface on which the load is being taken. Okay, so the F, when you are applying symmetry, means F by 4. We will be considering F by 4 load only. Okay, so we are asked to determine the radial displacement delta of the point from where the F is applied. Okay, what is the radial displacement exactly at this point of application of force? Then the dimensions are given here. This is the property of aluminum alloy. So we are going to use the aluminum alloy property here, and length is given, radius is given, and thickness is also given. So if we consider T by D, okay, T by D, thickness is 0.094 and radius is 4.9, that is approximately 5, so 10, it is less than 0.1. T by D is less than 0.1, so it is a thin shell and thin shell. So basically, you can go with the shell element idealization. Shell element idealization. F is given as 100 pounds, correct? So 100 pounds means what we can do is, what we are going to do is, we are going to take F by 4, that is 25 pounds load here. Because, yeah, because we are going to consider 4 pieces and all the 4 pieces are going to take that particular load uniformly. In general, we will not prefer point load, but given the condition here, we are going to consider the point load. Okay, given the condition, we are going to consider the point load, but in general, we will not be considering point load as it lead to degeneracies during the analysis. Okay, so we will now proceed ahead with the analysis part of this. Okay, always keep in mind what are the criteria if the model satisfies the criterion of using shell elements, that is based on the shell theories. Okay, you can simply use it as a shell. Try idealizing it as a shell. Next, shell element has basically 6 degrees of freedom at each node, 3 displacement and 3 rotation. UX, UI, UZ Rx, Ry, Rz. Okay, 3 displacements and 3 rotations. So when we are applying symmetry, for example, about xy plane, I am planning to apply symmetry boundary condition. Okay, that means the node should not move in the z direction. All the nodes on xy plane should not move in the z direction. Okay, that means uz will be 0. Okay, suppose if there is a rotation about x or y axis, again there will be a movement about xy plane. Since the entities on this particular xy plane, nodes on the xy plane should not move out of the plane. Okay, rotation about x and rotation about y are also 0. So for xy plane symmetry, Rx, Ry and uz are 0. Similarly, xz plane, Rx, Rz and Uy will be 0. So like that we will be considering the symmetry boundary conditions. So there is, we will not be directly applying symmetry, but rather we will be applying it in the form of deformation. Okay, in the form of displacement constraints. In the form of displacement constraints, we will be applying it. Now, I'm going to take static structural. Keep in mind, when we are using shell analysis, it is a three-dimensional analysis. So, for geometry, it is 3D. There is nothing to be changed here, the properties. But in the engineering data, we need to add aluminum data. Right? As the material is aluminum. So, go to engineering data, general materials, aluminum alloy, add it. We don't want this particular one, right? So yeah, we'll just come out. We'll just say we don't want this. If you take this, we are not going to send this particular material information into the analysis part. Okay, we are going to take aluminum alloy. Okay, this is what we are going to take. Now I'm going to close this. I'm going to come to geometry. So ఇది ఓపెన్ అయింది కదా. Now since we have opened this one, I will be creating the geometry. First and foremost, our units are in inches, so we need to change the units to inches. So yeah, inches, we are now in inches. Then yes, I'll select xy plane. I will create a sketch. Okay, I'll go to sketching. I'll select a circle. Okay, and here radius is given in the problem, correct? Right, we will not actually go with calculating the dimensions, rather we will. So 4 point something is there, it is 4.953. Okay, now what I need, only quarter circle, right? So go to this remove this and this. We are done with the modeling. Okay, click on the ball to get the ISO. Now select the sketch. Go to yes, extrude. మనం అర్థం కాలేదు. See, okay, the L by 2 is the length to which we are going to extrude here. See, L by 2 is the length to which. So 10.35 means 5.175. 5.175 will be the length. So here apply, we are extruding the sketch. Depth is 5.175. Okay, then yes, as a thin surface, it is there now. This one, say it as yes, and make the thickness as 0. Okay, and say generate. We have the surface body. Okay, now you specify the thickness here. How much thickness are we given? 0.094. Okay, 0.094 is the thickness that is given. Yes, we have. See, sorry, I don't think we will give the thickness here. We will rather give the thickness on the there in the mechanical. So if we give the thickness, we're converting into a solid body. We don't want a solid body, rather we want a surface to use the shell elements. Let us close this and let us open mechanical. Okay, now what we are going, we have opened this, you can see here. Okay, the shell for this. Now on the surface body, give the thickness as 0.94. So yeah, and add the material here assignment, take it as aluminum alloy. Now we have aluminum alloy assigned here. We need to see it as thick shells and thin shells. Thick shells. Go to thick shells and beams, and then after meshing you will see the effect. Okay, so now right click, insert face meshing. I'll select this. Since this has only 4 sides, 4 edges, I can go for a mapper face meshing. So yes, mapper face meshing, and then yes, right click, insert sizing. Okay, map and regular mesh. Is nothing but map mesh. You'll see the difference. Element size, not element size, rather, sorry, element. Okay, sorry, I need to go with the line selection. So yeah, insert sizings, go to line selection here, edge selection. Say Control A, 4 lines, 4 edges will be selected. Instead of element size, give the number of divisions, say some 15. Okay, and then say right click, generate mesh. See, you can now see it has a thick shells. Actually, it is not thick. This is your mesh. You can see how regular the mesh is. Okay, now we have to create uh, the symmetry boundary conditions, right? So for that, first initially I'll start creating named selections of each edge. For example, this particular edge is going to be in YZ plane, correct? So yes, so I'll select that edge, right click, say create name selection, YZ line. This one, right click, name selection, XYLINE. Some name you can give. I'm going to choose it for name selection, XZ LINE. Now what I'm going to do is these 3 name selections. I'll select this, create a nodal name selection, rename XZ nodes, YZ nodes. First one, na? YZ and ODS. Next, right click, create nodal name selection, right click, uh, rename XY and ODS, and then right click, create name, nodal name selection, right click, uh, name XZ and ODS nodes. Okay, now I have 3. Now right click, right click, insert. Yes, we don't want the commands, right click, insert. So go to nodal displacement. You can see here, right? Okay, here first let us deal with the YZ nodes. Okay, YZ means X should be 0. Okay, now right click, insert nodal rotation. Take YZ, Y X should be except as others are fixed. Okay, so let us say rename Y YZ disc. Okay, YZ root. I'm going to use it like this. Okay, next right click, insert model displacement xy, that is 0. Insert model rotation xy, so that is free. Okay, rename xy rot, rename xy this. Okay, then right click, insert model displacement. Okay, last one, nexted. Nexted means y is 0. Then model rotation. Nexted nodes x and z, y is free. Okay, so rename xz is xz already. Okay, now we have given the displacements, that means we have applied the symmetry conditions here. We now need to apply the load. The load is 25 pounds. Okay, so first and foremost, go to home, change the units to your inch. Take care that this is there. Okay, then see, when we go to this, these are the three regions we have considered. So the load should be in this particular point, correct? So what we are going to do is go for point selection, select this particular point, say right click, insert force. We need the force in negative y direction. Go to components, negative y minus 25. Okay, so we have applied the see, look here, we are pinching it, right? So it should be into the cylinder. Okay, supposing that if you are applying the load here at this corner, it should be in negative x. Okay, but where, so anywhere you can apply any convenient point, depending, as long as your point of application is correct or idealization is correct. So now I'm going to solve this. Okay, the solution is done. You can see here the solution is successful. Right click, say insert deformation. Our point of interest is deformation, right? Total deformation, evaluate all results, and radial deformation is what he has asked. So directional deformation in direction of y and the direction of application of force. So deformation directional, all bodies in direction of y axis. Say right click, evaluate all results. Total deformation, we needed radial, this one, right? Okay, the point of application of force is this one, I believe. Here. Okay, so total deformation here, if we look at it, we can see that the maximum is 0.11374. Okay, what is the solution value he has given here? This calculation 11391 is what he got. We got 11374. Yeah, okay. It all depends on meshing and other things. Okay, this is what he has computed manually. Okay, we can also do some fineness. We can increase the fineness, like edge sizing, instead of 15, let us take 30. Right click, say generate mesh. Right click, clear generated data. Right click, solve. So Basically, yeah, it depends on the meshing parameters and other things. How can take a meshing and other things. We took the meshing in a different fashion, maybe. So with this, the shell element. How to use the shell element? I have seen. Okay. So yeah,